Welcome to this short course on materials for green energy, for alternative energies. And it's for me a pleasure and honor to introduce you to our talker, our teacher for this subject. Edgar Lara Curzio is a big, large, very incredible person, and also a very good scientist. And very, very good teacher. I'm not going to talk very much about him because sure that I will need 1, 2, 3 hours, because he has done a lot of things in science and in technology, because he is in one of the best places to research in the world, that is Oak Ridge National Lab. He is originally from Mexico, but he has been in USA, I think,
since 1986.
A very long time. I hope that you could discover him, because he's a really very, very nice person, and sure that you are going to learn a lot of things with him. Thank you, Edgar, for coming, and the time is yours.
Thank you. Thank you.
Welcome.
Well, it's a real pleasure being here today. I love every chance I have to come to Spain. For the next 4 days, we're going to be talking about different materials for energy. And we'll be talking about composites. I prepared some notes. Tomorrow we'll talk about composites. We'll also talk about some functional materials. So I hope that the topics that we will cover this week will address, and you will find them interesting. Let me tell you something about myself. I got a degree in engineering physics from the Metropolitan University in Mexico City back in 1986. I went to the US. I got a PhD in materials engineering from a school in upstate New York. It's called Rensselaer Polytechnic Institute. I finished my degree in 1992. The topic of my thesis was studying ceramic fibers. There was a particular fiber called silicon carbide fiber that is used to reinforce ceramic materials for high temperature applications. And most of my work for my PhD was focused on materials for propulsion, in particular ceramics for gas turbine applications. And later on Thursday, we'll talk about gas turbines. And I'll give you some examples of how that research that took place 25 years ago is now being used in commercial aviation. General Electric just announced a few months ago that the engines for the 737, the Boeing 737, is going to incorporate some silicon carbide matrix composites. And that's really a breakthrough for civil aviation. These materials have been used in military aircraft engines for a while, but I'll share those experiences with you. When I finished my PhD, I moved to the state of Tennessee in the southeast, and I joined the Oak Ridge National Lab. The Oak Ridge National Lab is the largest multi-program science laboratory in the US. And it was established back in 1943 as part of the Manhattan Project. The objective at the time was to develop the atom bomb. And at Oak Ridge, there were 2 important missions. The first one was to demonstrate that you could operate a nuclear reactor. And there was a very famous physicist. His name was Enrico Fermi, who was a professor at the University of Chicago. And he came to Oak Ridge, and he was very involved in the construction of this facility. This is a so-called graphite reactor of the Clinton pile. And this was the very first nuclear reactor that operated continuously in history. And that was a major breakthrough. And what was important about this experiment is that they showed that if they could put uranium into the reactor could operate in a stable fashion, and it would produce plutonium as part of the nuclear reactions. And that plutonium was eventually used into the bomb that was used in Nagasaki. But by showing that it was possible to do this, they copied this model. And there is a laboratory in the west coast of the US. It's called the Pacific Northwest National Lab, where they built several of these large reactors to produce plutonium during the Manhattan Project. So that was the first thing that Oak Ridge National Lab did for the Manhattan Project. The second part was to separate uranium isotopes for a uranium bomb. And if you mine uranium, you will find that 99.3% of the uranium that you get is a special isotope, is uranium-238. And there's about 0.7% of an isotope called uranium-235 that was the interest, the one that was of interest to make a nuclear bomb. And then in Oak Ridge, they established a factory-size facility to separate isotopes of uranium. And that's the bomb that was used in Hiroshima. So those were the origins of the Oak Ridge National Lab, 1943. Obviously, in 1945, the war ended. And then one of the questions is, what do we do with the national labs? And even though the origins of the national lab were military, based on nuclear energy, today the labs have been transformed. This is a picture of the Oak Ridge National Lab. It's a fairly large facility. We have a $1 billion plus budget, so $1.2 billion a year to do research. We have more than 4,000 employees. We have 3,000 visitors. Teresa was one of those visitors. We have the fastest computers outside the classified world. These computers are being used for a number of grand challenge scientific problems. We are also responsible for the participation of the United States in the International Thermonuclear Experimental Reactor. There's a tokamak type of reactor being built in Cadarache. And then the US is an active participant, and the Oak Ridge National Lab manages the participation of the US in that program. We have a world-class spallation neutron source. This facility is used to investigate the structural characteristics of matter. It's a world-class facility. There's one built here in Europe, Denmark and Sweden. I don't know if some of you are involved. And this is the type of facilities that will help push science to the next level. Obviously, we are well known for our work in materials research, and today I want to share some of that with you. And as I had indicated, we are the largest energy lab in the US. So when you look at the mission of the lab, what we do is energy security and national security. That's really what we do for a living. And we have 6 core competencies. Number 1 is we drive science when it comes to a neutron. I mentioned the spallation neutron source. We also have a nuclear reactor called the high flux isotope reactor that has the brightest beam of neutrons that we can use for the structural characterization of materials. I mentioned the computing, the high performance computing capabilities that we have. Most of the work that we do in materials is for energy applications. So everything I want to share with you this week is going to be focused on how we use materials for energy. And I mentioned that the origins of the lab go back to the Manhattan Project, nuclear energy, and we continue doing a fair amount of work. We're not going to talk a lot this week about nuclear applications, but I want to mention this morning some of the projects in which we are involved, because we do believe, despite everything that has happened, Fukushima, Chernobyl, there's still a role that nuclear energy can play, okay? And we'll talk about that. And obviously, when it comes to energy, we are there. And for national security, we do a lot of work. So what are we going to talk about this week? Well, in conversations with Jose Ignacio, today we're going to talk about projections for how we are going to use energy in the future. And I think it's important that we talk about this at the beginning of the course, because when you become professors or researchers, and when you write a proposal, in many cases you have to justify why you're going to be doing research. And the material that I'm going to show you today provides a good framework for what type of problems we should be tackling. And that's what the topic of this morning's discussion is going to be. I'm going to give you a quick overview of energy technologies, and I'm going to give you a snapshot of how those technologies are being used in the US and what is the motivation for furthering developing those technologies. And we're going to talk about a very important topic. Spain is facing some challenges. In the US, in the West Coast, we're facing some challenges, and that's the so-called water energy nexus. It has been shown that water and energy are interconnected, okay? And that poses pretty significant challenges, and I'll tell you what we are doing in that area. Tomorrow, we'll talk about composite materials. Some of you mentioned composites as the topic of research. I'm going to give you a general overview of the types of composites that we are working on, how you can calculate properties, how do you design components using composites, and I want to show you an example of how we've used everything that we've developed in terms of theory for composites towards wind energy. And in fact, when you analyze a wind turbine and you do the structural analysis, you realize that all of that is going to be limited by the properties of this material. So that's going to be the focus of tomorrow's talk. On Wednesday, we're going to talk about solar energy. When we talk about solar energy, we talk about photovoltaics. That's a way to convert electromagnetic radiation into electricity. But there are also other technologies, in particular concentrated solar. In fact, Spain is a world leader when it comes to concentrated solar technologies. We'll talk about photocatalysis, and we'll also talk about hydrogen. If you ask people, especially in the transportation industry, what is the future of transportation? They want to tell you that the electrification of transportation is really the ultimate goal. But there's still a group of people who believe that hydrogen is going to be the fuel of the future. So we'll talk about that tomorrow. We'll talk about the challenges when it comes to producing hydrogen, storing hydrogen, transporting hydrogen. There are some significant challenges, and we'll review those. And then on Thursday, we'll talk about energy efficiency in general. Okay, that's the low-hanging fruit when it comes to solving problems. And I'm going to spend some time talking about thermoelectric materials. This is one of the most fascinating classes of materials. I don't know how many of you have been involved with thermoelectrics. Even though we have known about the thermoelectric effect for almost 200 years, there are some great opportunities. And I'm going to show you some examples of how we have been involved with NASA. If you have heard about the Mars Science Laboratory, have you heard about the Mars Science Lab? There's a rover moving on the surface of Mars right now, and the power supply is a 225 watt power supply that uses isotopes of plutonium-238 to generate a lot of heat, and then using thermoelectric materials, we're converting that heat into electricity. Those materials are not very efficient, but nonetheless, they are very reliable, and part of the research that we are doing is trying to develop a new class of materials, including materials that do not exist in nature, okay? And for that, I want to talk about this topic of design of materials, where you utilize things like quantum mechanics and some principles based on the electronic behavior of materials to design, again, materials that do not exist in nature, but that can have outstanding functional properties, in particular when it comes to converting heat into electricity. Most of you took thermodynamics, and you will see that we waste a lot of heat. So being able to recover some of that heat could be a tremendous opportunity, and that's an area of active research. And I'll show you some examples, including recent publications that we have done in the area of thermoelectrics, where we believe we are on the path to breakthroughs. We'll talk about gas turbines, and I mentioned the work on my doctoral thesis with ceramic matrix composites. I'm going to show you some examples of how we are using thermal barrier coatings, CMCs, monolithic ceramics, to improve the efficiency of gas turbines. And again, in civil aviation, there are some great systems that are coming online. And again, this is all thanks to materials. And again, we'll close on Thursday talking about this new area. Given the power of computers, high-performance computers, it's actually possible now. It's going to be more and more frequent in the future that we're going to be able to design materials, again, materials that do not exist in nature. And all you have to do is outline the goals. So, I want a material with this thermal conductivity, this yield strength, this elastic modulus, and then using theory, we're going to be able to come up with those materials. So this is an area that's really going to revolutionize material science and engineering, and we are already seeing some breakthroughs, and so I'll share that with you. Any questions? No? And I'm flexible. If there is a topic that you would like us to discuss during these days, just mention it. I got some material, and I can put together some slides, and we can talk about that. Okay? So we have some flexibility. But this is a general overview of the topics for this week.